so we can wait a couple of minutes and get started. So today we have two sessions on GMAP that are of course related. One is before the coffee break, the other one is afterwards. In the first one, we will have some general presentation of GMAP and introduction that Riccardo will deliver. We will have some input from previous participants to the winter school, particularly the one of this year. I think Scott Mansfield will present that, and then we have two presentations of Carlos describing the services that have been built through the years within GMAP for the community to use. Then there is a break, and then we have few exemplary mapping projects that have been developed through the last couple of years or so. And we also have some of the tools that have been developed and released by GMAP that can be used to aid the geologic mapping process. So Rick, just take the stage and tell me when you wanted to change the slides.
So today we are introducing the Europlanet GMAP, which is a geologic mapping research infrastructure within Europlanet. It's led by Angelo Piorossi and Matteo Masseroni by the University of Padova, Constructor University, and me as a deputy. And if you go to the next slide, I will explain a bit the rationale behind GMAP and what are the services that we are providing to interested users. So far in the last decades, we got many space missions. We got many data from planetary surfaces, both like imaging, spectral, LiDAR, so topography, images for high resolution targeted locations, and so on and so forth. And the upcoming missions are building up from those type of images with respect to where we can go, where we can land, what are the things that are relevant to observe, where we can sample, where do we want to target our high resolution observations, not to lose data volume, etc. And this is why geological mapping is very much useful. And there are many mapping products. There are global mosaics of planetary surfaces. There are more targeted images. But essentially, in the past decades, the only ones that were doing planetary surfaces geological mapping in a structured way were just the United States Geologic Survey. So the idea was to build up a network and an infrastructure to sustain a European effort in that view, since we also have missions that are mapping planetary surfaces. But geological mapping was done in bits and pieces, the universities, the research infrastructures, research centers, and so on. But we wanted to gather all the knowledge and also to attract new people, newcomers to provide mentoring, tutoring, and help and resources in order to do it in a more consistent and structured way. Of course, what we want to do is to apply the basic geologic mapping principles in terms of superposition of events, geomorphology, stratigraphy, and so on. And we want to spread this mindset as much as possible. We have to apply it to planetary contexts. This is a really nice presentation that Angelo put together with some interactive moving of models. And so, as I said, we want to foster this mapping effort and to provide guidance and tools, because I remember also myself when I was starting my PhD, I was a bit confused, like, where do I get things? Where do I get information? How do I do this thing that for other people is very easy and I don't know where to start from? And we want to build this sense of community and a real community to support this mapping and training, and to provide everyone with the same set of skills and tools in order that the mapping is done quickly, efficiently, and in not in a standard way, but in a let's say hitting some standard quality levels. And of course, we got also the engaging with the agencies like private companies, etc. As I said before, very briefly, that the geologic mapping, of course, is a lot about scientific investigation, but not only, especially nowadays that we are talking about the space economy, we are talking about getting back to the moon, mining asteroids, and all these kind of things. We just need to be aware that science is a big thing, but also there are entities that are interested in other things, and science is like opportunity, science of opportunities, collateral, but they want nonetheless to have an idea where to focus their attention to. And geologic maps basically are the sum of all the characters of a planetary body that can be useful for risk assessment, landing target assessment, etc. And of course, environmental protection as well, because there are some places where you do not want to go to preserve the environment, to not contaminate with objects coming from the earth that are bringing bacteria or like pollutants to potential ecosystems, for example, on Mars. So this is basically the major points that are giving a rationale to why geologic mapping is still nowadays important, not just 200 years ago or 100 years ago, but nowadays is also a big thing. As I said before, we are standing on the shoulders of giants because USGS traditionally was the first one implementing a structure mapping, planetary geologic mapping, of course. And they have built that with the heritage of the Apollo mission. So the big effort to bring the humans to the moon in the late 60s, as an outcome, has also had the very first planetary geological maps. And they are fostered and supported not only by the government, but also by the community. There are the community and scientists that gather and got the USGS, let's say, under the USGS umbrella, and build their own geologic maps. We are instead building, and we are not jumping on the shoulders of giants because we were not giants, but we had this project, this European project called PlanMap, which was one of the first efforts on an European side to build innovative geologic maps. So to gather all the information from morphology, spectra, put them together into geomorphospectral, etc. maps, with also a 3D perspective, like trying to reconstruct the subsurface with 3D modeling techniques at the local scale, at the global scale. And we were starting with this project to cluster the first European actors. We had in the consortium, we had like UK people, German university, French university, Italians. And then in GMAP, we have also other actors, like, for example, the Polish Academy of Science, etc. And the approach we followed was to be as open as possible. So every tool we used, every procedure we used is open source, is documented, the codes are available in GitHub and so on and so forth. And this is more than true for the GMAP infrastructure. So if we are providing documentation and guidance to do a specific types of mapping, a specific type of data exploitation or processing, or techniques to create base maps, or some software aids, like software that we built for helping in mapping, you will see it later, or web services that are available from outside. Everything is open source, is documented, is available to the community. So in line of principle, nobody has to pay for anything, because all the softwares and techniques we are providing are available to anyone in the world. And this is more than true because we also are providing training and community support, and we don't have to assume that everyone in the community has access to the same type of resources. There are many, many different countries with many, many different type of resources that they can allocate for planetary mapping. And if we are as open as possible in terms of tools and softwares, we are more than sure that we can gather more and more actors into this community. By the way, Andrew, you can stop me if I'm saying incorrect things.
Everything is perfect. Thank you, Riccardo.
You're too kind. Documentation and guidance is the very first thing. This was something that was really scattered around the internet, and we are creating structured introductory guides. We are gathering also existing resources from outside that are maybe not easy to discover, or they are like spread around the internet. We are gathering them into our hub, so that we are creating brand new introductory guides, but also all the outstanding existing documentation. We are basically pointing to that documentation, so that if you reach our website and our documentation page, you will have a sort of a hub pointing to our resources, but also to other resources from other actors. And this is a demo of the wiki we have. So we have a wiki with all the community mapping projects that we are sustaining, but also inside we have all the tools and the guidance that we are providing. So a wiki is also an important part of our of our infrastructure. You see here, for example, we have a page for 3D geological modeling, where we introduce what 3D data is, what are the most useful formats to do that, what are the basic techniques, basic softwares. We have software guidance to build the first 3D geologic models. This is another, for example, section for map projections, how to build the base maps, how to do that, what are the already ready base maps, what are the relevant things to know about map projections in building a base map mosaic in a nice way. What are the online tools already existing that are able to exploit global mapping products or global images products, etc. And also other types of materials. So if you go to Europlanet website, europlanet.gmap.com, I think, you will have access also to all of these tools. And apart from tools gathered or built by us, you can also have access to brand new services, and Carlos, I think, is going to talk about it later. So we are providing also a tool, an infrastructure to exploit and use ISIS, for example, through a Jupyter hub system. We are built a software, I will give a demo of this, to do effectively and quickly mapping without losing time in creating topologically correct polygons or lines or whatever. So there is a plugin for QGIS, open source. One can take and modify it. You can use it. And it's built into QGIS, which is, again, an open source software for mapping, which is supporting more and more planetary mapping, map projections, etc. This we will have a demo of this, I think, like at 11, yeah. And then, of course, crater counting. So crater counting historically was a method that relied on softwares that were not open source, but open to the public, so available to use. But some of these tools were integrated into ArcGIS, and you know ArcGIS is like the golden standard of the industry, but it's very, very expensive. Now this, for the first time, has been translated into Python, and we have now a plugin for QGIS to do exactly crater counting with CraterTool. So the same tools we are already using since, I don't know, 10, 15 years, but now it's ported to QGIS and to Python, and one can use it via command line, via Jupyter, or via QGIS into its interface. So this is a very brand new thing and very useful. And of course, web services. We have also a data portal, a wiki, a Git, where all the code is available, and you can pull it and modify it, and a Jupyter hub system. And I think we will go quickly on that because Carlos, you will say more about it. But this is a demo. Base mapping, I already mentioned. We provide base maps, but we also provide training. So it's not only that we gather information, we store them in the website, and that's done. We do yearly a winter school. Now we did 3 editions so far, and about planetary geologic mappings, but also on analogs, and is held every end of January, early February. We had consistent numbers throughout the years. First year was during the pandemic in 2021, and we got like 200 more subscriptions. We thought, this is because people has nothing to do at home, so this is a nice thing to do. But then the second year we got more than 300 people, and this year we got 400 more people participating to the school, some of them live, so real time, some of them asynchronous, because this is offered online for a reason. It's offered online to be as open as possible. We are using open source tools, but we are also doing it asynchronously. So one, if he has time, can do can follow lessons and hands-on activities live, but everything is recorded real time, edited on the fly, and then put on our website. So people can join later and see exactly the same things and can also interact with the community. Everything we are providing, we provide data sets for training, we provide guidance for training, a bit of introductory lessons, but the nice thing is that we also have a community built on a Discord server, so one can interact with instructors in real time, just typing on a chat, just making direct calls, and lessons are there. So people can go on the website, can follow lessons, can pull the materials to exercise, to practice, and in the end can reach out to us if any problems arise. This is a bit of the scale of a schedule. First year we had like 30 more instructors, and then throughout the years we were about 20, so between instructors and coaching during the hands-on activities. And from that, we started to build up the community. So we do community mapping projects. So there are projects that are sustained by people that are within this infrastructure, let's say, that are using resources of this infrastructure, either talking to us or getting information from our websites. Or so, yeah, better, okay. And if you go to the wiki, there are an example of the projects we are sustaining or we sustain. Some of them are finished, some of them are active, some of them are a bit dormant, but still, these are a few examples. This is published, for example, Health Crater. This is going to be published soon, I hope. Spinaton Tesson by CBK Pan. Holden Crater on Mars. Tsiolkovsky Crater on the far side of the moon. Published the Valentin Domes, which is an ongoing work on the lunar near side. This is a very nice map of a planetary analog. See, this is the northern part of the Lanzarote Island by Ilaria Tomasi. She did a very, very beautiful job of mapping this volcanic field. And of course, all of this data can be published and shared. We have a data portal where you can gather or pull all your data. And we also have a Zenodo community. So what does it mean? It means that although, even if you publish your own data outside GMAP, but you want to use this infrastructure to make the public more aware of your work, instead of storing it, I don't know, in Figshare or in some private repository at the university, you can publish your work, you can have your own DOI, but you can provide it to us so we can put it in our portal and make it more discoverable. So this is not just for the maps built for GMAP, but also for other actors or other people that simply want to be more discoverable. So we are creating also a hub to gather information and products about, I don't know, base maps, mapping products, sharing articles, etc. And of course, this is integrated in the Zenodo community within Zenodo itself. So it's much more easy to find it consistently within this community rather than looking for a single product which is somewhere inside the big Zenodo bucket, let's say. We have a mailing list that you can join. We have a monthly call, so every month, typically I think it's the first Thursday of the month or something like that. We have a community call, so you can join. It lasts 1 hour more or less. You can talk about your mapping, the problems that you have, if you want some advice, if you want to gather more information. And this is creating also nice interactions between the users, because some of them then started to cooperate between themselves. And we are always there, so we can provide advice on the fly. We can arrange more dedicated telecons, but it's a nice way to see what is going on within the community. We have this Discord server, of course, and if you want to get more info, you can go to this website, so Europlanet-gmap.eu, and the planetary mapping school is planetarymapping.com. And 2024 winter school, we are organizing now, try to build up the schedule. I think it would be as before, like late January, early February. Just as information, the first year was about heritage of plan maps, so 3D mapping techniques. The second year was about more consistent mapping of Mercury, Moon, and Mars in a more broad way. This year was about mapping for landing sites. Next year probably would be about icy satellites, minor body, and Venus. We will have to see. But every year we try to shift a bit the topic so that it remains interesting, and most of the people are joining throughout the years. And it's free. We're not making pay people for this. Okay. Angelo, you can add something or?
No, actually, that was perfect. Thank you so much, Riccardo. And I think that was good. Also, it leaves some time for Scott, who wanted to
yes,
discuss something about the last school. And yeah, I think that for the rest, I think Carlos can show better than what I can say now.
So we have Scott Mansfield, which is one of the alumni of the school, who wanted to provide feedback for what he saw in the past years. Thank you, Scott. You can go ahead if you're there.
All right. Okay. So there. I wanted to just give a little bit of feedback briefly on my experience with the school. I attended in 2022 as well as in 2023. And my experience with it has been that it's been both years very well organized, very well curated. The hands-on activities are a really good introduction for people who don't have a tremendous amount of experience with GIS, while also providing a lot of opportunities for people who are experienced with GIS to work on new tools they may not be aware of, which are discussed in the lectures. It also provides a really good tool for disseminating some of those new tools like Mappy and Jupyter that Europlanet has been working on that people may not be aware of exactly how to use, maybe to get over the hump of intimidation to avoid falling back on old tools. That can be very useful in getting new techniques out to the community. I just wanted to show briefly, so here's one of the hands-on activity maps that we did this year. This is what I ended up with. So we did Copernicus crater, and we ended up with a pretty extensive maps of melt pools and contractional fractures from melt cooling and so on. So the activities are detailed enough that you can really get quite in depth into the mapping if you choose to do so, especially if you continue working on it after the school, which of course is always an option. So I think it's a very good opportunity for people who want to get some experience with GIS, want to network with GIS professionals in planetary. And I think it's also a really great opportunity for people who are international and overseas, especially outside of Europe, as far as an outreach activity and an educational opportunity for them. So that was what I have.
Okay, thank you, Scott. Angelo, is it me that present now? What do you have in your agenda? Yes. Okay. Okay. Cool. Thank you. Okay. Hi, everybody. I'm Carlos. We met. Some of us met during this week. I am now going to present some of our tools that we have been developing in GMAP. Thank you. In the last few years. So we there at the Constructor University, north of Germany. The group is me, myself, Angelo is leading, and Giacomo is also working, is a very important piece in this that I'm going to present. We work hand in hand in developing some of these systems. And as you see there next to the screen, a poster for the Explorer. This is also Giacomo is working there, and then later he will talk and good stuff. So I will present here. So this is the roadmap. We will split that somehow. Maybe we will just go up to the coffee break. I don't know how time is it now, but yeah. Or maybe we will break this thing into sessions. Don't know. Let's see how that goes. So the first thing is I'm going to. Riccardo just gave a overview of tools and interfaces that we put in place for GMAP. I will focus and I will go briefly on that from the infrastructure point of view. So I'll go a level lower, talking about systems and some of the technical purposes of those systems. And in particular, I will focus in two of those tools or interfaces, which is the data analysis or data processing hub and the data portal. Right. So what are my goals here? My goals here is to present some awesomeness, obviously, of our work. And I would offer you, so things that may be useful to you is to offer this, in particular, the data analysis hub that we built, that we built so that thing we could scale up, as I will talk, and individuals could use that beyond the premises of Europlanet and GMAP. So for yourselves. And hopefully motivate you to contribute either with requests for features, reports on bugs, or just using our stuff. That's the way to progress. So that is honestly my ultimate goal, to have you, your input, output, this thing in this community, so that I can use your points of view to make our systems better, right? That's all about open source, and that's what I personally want. So a big view of our infrastructure you see here. So as Riccardo said, we have website, wiki, blah, 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 blah. And here is from the systems perspective, right? So how those pieces go together. In a simpler view, we have, let's say those are the main components in our premises. So the website, I will not go again, just here some links for you to go there and get to know. The wiki, as Riccardo said, has documentation and detailed information. One of the things that we put up there is, as we see here in the lower, so the lower level of this picture here, GitLab, Invenio, and Jupyter Hub, let's say, are the most technical from the computing point of view. And reasons for that, for instance, for GitLab, we use GitLab for multiple things, mostly or generically for project management. So we use issues there to bring discussions, to solve discussions, make actions on people, on ourselves in many cases, so we can keep track of that. Like GitHub, for those that are used to that, we put that in our premises for two reasons. One, so we could do the math that we want to do without showing that to the outside world. So this is for code repositories and data and as I said, actions for internal use. Then we can split that however it fits our needs. And also for user authentication. So we use the server that GitLab provides to allow users, well, to do proper and unique centralized authentication in our systems. And then those are those two systems that I will talk further from now on. One is our Jupyter Hub for interactive data analysis and to simplify the deployment of processing tools, and then the second one, the data portal. Right. So first of all, the Jupyter Hub. What are the motivations for Jupyter Hub, Jupyter Notebooks, and this system that we put there? One of probably the major motivation is to remove software setup boilerplate, right? So we spend a lot of time, every newcomer, every visitor, every collaborator spends a lot of time setting up software, and that may be even too complex or error prone to many users, those that are not really into systems and installing stuff and configuring complex systems. For instance, ISIS, the integrated software for the spectrometer and imagers. ASP, the stereo pipeline. You put that, this thing has to work with GDAO, and then nowadays we do a lot of Python stuff. Rika showed before QGIS. Probably all of us here know and use QGIS at some level. But these days, the Python data science stack is everywhere. Probably most of us use that. We certainly do that in Constructor. And so the thing on setting up systems, they can get very complex very quickly. Either because, again, you are using these multiple libraries, multiple versions of softwares that is common in Python, or because you're using legacy software. So one of the things is to simplify this thing. The other thing is to homogenize versions. And this is important, again, especially for data reproducibility. Every software version comes with features and bugs. And when you do results, when you collaborate in a pipeline where you and your collaborator or collaborators don't share the same software version, you may find yourselves eventually looking for a data bug in the worst case, or a difference in the data that it's hard to track that down. So that comes directly to the argument of data reproducibility. And it cascades to, again, productivity and efficiency in collaborating. And then the third point that I have there that effectively I like very much is scalability and portability of software. So not only you would like to have a place where things just work, but you would like, we here, many of us, all of us, some have it here in our tables, have different desktops, some running Mac OS, some running Linux, Windows, and then we go to our universities, there is a desktop workstation. Some of us have has a cluster to run stuff, so you have different systems everywhere. And these days we even have cloud platforms. That's, for example, in United States, they are getting more and more with cloud contractors, cloud platforms, offering infrastructure as a service, and then running things on the cloud. So software is moving a lot these days, and there's a big discussion behind that, which is what should we move, data or software? And seems fairly clear to me that the conclusion, although not explicit, the conclusion is to move the software just because it's cheaper. So we have to work that out. So brief introduction, what is Jupyter Hub? I don't know if everybody here is familiar with this thing. Jupyter with Y is the software where for interactive data analysis. So we use mostly, this thing came from the Python community. Nowadays, you can use other languages inside this, this environment. Hub and lab or notebook, as I put there, is has a subtle distinction. Lab/notebook are basically the same thing, just lab is a newer version of notebook. And this is the, right. And this is, so everybody saw the message from Angelo. And this is effectively where you run your code and you document. This is super cool because it's a way for documenting as you code. And it goes in the data storytelling paradigm that the data science community have been developing in the last few years. The idea and the solutions for that. So the hub is something that manages multiple notebooks or labs, if you will. One of the things that the hub does is to handle user authentication, right? And then once the user is authenticated, it spawns the corresponding notebook. And then behind the Jupyter Notebook, we have this thing. This is the schema that we have in there, right? So, okay, so here you can see. So here you have the hub. The user comes here from network. Let's change that for internet. The user comes here and finds the hub, authenticates, and the hub spawns a Jupyter lab, right? From a different view, here is what is going on. And then once this thing is spawned, the user is there in his or her private environment. So each of those things, each one of those symbolic notebooks here, this rectangles here, is a private box with its own resources and privacy, if you will, which is it may be not very important if you work in with your close friends and your group, but it is important when you go to clusters and cloud environment. We do want some privacy. And then outside of this, this rectangle here, where the data processing is, we have the user space, and this is the storage. Part of that is, again, private, and part of that is shared. All right, so here for each notebook, for each user, actually, you have a private storage space, which no other user can access that, and this thing persists. So you shut down your notebook, you go on vacations, you come back, your data and your settings are there, right? Then we have some shared data storage where you can exchange data with your colleagues. And then we have some read-only data, for instance, ISIS data or any other ancillary data for your data analysis that the system administrator, for instance, I have to provide so that notebooks work properly, right? Right. So going back to this thing here, and then there is this aspect of scalability and portability. Remember what I told at the beginning is that I want you to use that in your own workstations. And if you have to run this thing here, that seems a bit too much. We don't need that, right? But the important part here that adds for portability is this thing here, right? The Jupyter Lab. And this is actually effectively the core of this whole thing. There's this whole thing. I was telling you that so that you understand there is, if you decide, and everything here is open source. So if you in your labs, you want to have this infrastructure, there is a GitHub repository, and accordingly, Docker images here that you can just download and run this thing. So you can have this, the whole infrastructure, but we don't want, not on our everyday stuff, right? This is the core of the system, where we focused on addressing the main software for planetary data analysis: ISIS, GDAL, ASP, and so on and so forth. Here's the repository for this this whole system I'm telling you about, which is in our the GMAP organization on GitHub. So again, this Jupyter Lab, the portability that we achieve here is through containers. If you're not familiar with containers, it's this stateful package. Basically, it's you can think of a virtual machine, but a lightweight virtual machine. You get this thing, you run, and things, voila, they start happening. It's beautiful because it's light. It's light. Our container is not that light because we have ISIS in there, and this thing is huge. But the technology is lightweight and portable, so we can do that in Windows, Mac, and then we stop worrying about where we are running this thing. And then, so there are two things here. One is you have this thing for processing data, and the second thing is you can and you will likely share data between your host computer and your container. So this container is running on a environment of its own. Whoever is inside that, and this is the privacy I was talking, does not see the rest of the whole system, which is good, but adds a boundary here, right? So neither the host can see what's inside the container, nor who is inside the container can see what's outside. So you have to share that thing. I'm telling that because if you start using, I hope that many of you start use this thing, and you are not used to, those are things to keep in mind, but they are fairly easy to, it's not workaround, it's meant for that. So it's fairly easy to make it work on your, for your very own use. Okay, so how do we use that? Blah, 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 Carlos. You have been talking now for 2 hours. How do we effectively use that? You say it's ready to use. Well, basically, we install this thing called Docker, multi-platform. We go there to Docker, we install this thing. There is a executable or a app that you bang, you install this thing. There is, for Windows and Mac, there is a graphical user interface called Docker Desktop. Linux, yeah, as we are all used to that, Linux goes to the command line, but that's fine. Still fairly simple. So we install this thing, you pull this thing that I'm talking about called Jupyter ISIS or Jupyter GSpy. We have two flavors of images, one focused on ISIS software, and the other one with Python data stack. We are merging these things, but the final images are getting very big. The ISIS image, when you download, is a couple of gigabytes, and when you unpack, and in your computer, you don't have to unpack by yourself. It does automatically. It uses like 4 gigabytes. And the GSPy, we are using a lot of well-known libraries. This thing goes with 1 gigabyte, so we are trying to merge those two things. Nevertheless, they are there for us to use however we want, and you can customize those things. That is one of the aspects that we took care of when we implemented that. And if you are going to use ISIS, you need to download ISIS data. I tried, but I tried to split ISIS data in many pieces and make a constellation of containers so we could just use. It didn't work. ISIS is fairly big. So we are talking here of some dozens, hundreds of gigabytes. Yeah, so this is one thing that you have to download if you're going to use ISIS. It's fairly easy. There is scripts for doing that, so this is not a problem. You download this data, you install Docker, and then you run it in more specific steps. Again, all the steps there, but once you have things installed and downloaded, you have those 2.5 steps to have ISIS. So now you don't go through a lot of installation, but you run it. You pull the image, you run it, and you go to your browser. Why you go to your browser? Because this Jupyter lab provides the processing functionality through web browser. Right. Okay. So, for example, how does this thing work live on those examples there, for example? And those links here. So here is the Europlanet, the link for the Europlanet organization on GitHub. I have it open here, right? So here it is. And here we have lots of notebooks. We have the repository for the container, and we have some some events like this one and the winter school material that we use, and tools, as Riccardo said. So for example, the OpenCraterTool, Mappy, and stuff like that. So you come here. This is for the geeks like us, software interested. We go here. Right, and here is in particular the repository for our stuff, for those containers. So effectively, what we have here is, okay, cool. Make this thing here bigger. Right. There you go. So as I said, we go there. So I have Docker installed. I have ISIS, although here in this little example we are not going to use. And I'm going to use this GSPy notebook. I have this thing there. GMAP, Jupyter, ISIS egal. I have already downloaded, so I'm just checking that thankfully I had already downloaded because the internet is not, well, have a lot of devices connected. This is one thing. In the meantime, here is, and those links are in the presentation, just to let you know. Here we have the repositories. For example, the repository for GSPy is here. This is where we are downloading our images from. And then once this thing is, as I said there in our presentation, we now run this thing. You can do that through the graphical user interface. For example, here in Docker Desktop, in Mac and Windows, you have those things here. Okay, let me do some cleaning here. I just got used to the command line. And then here I'm sharing, for example, here I'm just sharing, as I said, a directory that I want to have inside my container. Remember, this thing runs isolated, and I want this thing to be there when I run my container. And then Jupyter GSPy is the one that I'm using. We run this thing. This thing gives me some messages, and I come here. I copy this URL from Jupyter. So those that are used to use Jupyter, this is the way it is. It has some kind of authentication here, and then we go to our browser, and voila, we have it. We have Jupyter running here. We have our notebooks where I can come and just run stuff and start running. Hopefully this thing runs fine, who knows. And so on and so forth. So apparently is doing some work here. We have some messages from GeoPandas, so on and so forth. Likewise, now going to our hub. And then we have, so this is one thing that works and you can all use in your workstations. And then what we have for a GMAP, specifically in our running, in our, let's say, in our cloud instance, in our premises, is this the Jupyter Hub instance. So for example, here, well, sorry, let me just go through here some of so for example, Jupyter, Europlanet, and when you come in there, you have this screen here, which is the authentication screen, right? So this is the landing page. We go there, we use our GitLab for signing in, and we go there to for our instance, we authenticate there, and this thing comes back to our Jupyter instance. Yeah, should come back. Eventually. And then here we have, in the meantime, it's just to if you deploy your hub, this is what's happening. You have this authentication step firsthand, and in our case, you can choose between the images, but that's it. We have some overload here. And then when you're getting there, when you land in, let me just break this thing. When you're landing there, you get this this screen here. So I have added a couple of things here already in my space, so I customize that as I go. Things persist, so this thing here will remain there as you work your data through and your research. But this is, you will have there a ISIS environment where you definitely go there for using ISIS. Here, for example, you have all the tools for ISIS, likewise GDAO, sorry, let me do that. Likewise GDAO stuff. GDAO translate should be here. Okay, now I have to check that. But effectively, you have the software in there, true for ISIS at least. I don't know where GDAO is here. And you have this this space here. So this is the work is your private space. Right, so in this directories here, these folders here, work is your private stuff. So whatever you do here, it's yours and yours only. Then we have this shared folder where people are free to put data in there and share with their collaborators. Obviously, data, software, whatever you want to share, notebooks with your colleagues, you go there and you share. Then you have the data space that you are using for read-only purposes. For example, it's not here, but ISIS data should be here. Okay, I forgot where things are here now, apparently, or mount ISIS. Yeah, ISIS data, it's here. And those things are all set in our environment already for our use. Right, so ISIS environment stuff are all in here. That's one of the reasons why I forget those things, because I set that and I can forget, which is pretty cool. So this is the whole of the tools, the whole of Jupyter Hub. In a nutshell, or not. So here we have, so for example, Angelo shared with me a notebook. Where am I here now? Right. So Angelo shared with me some notebook. And then that he developed either in the cloud or in his own workstation for that. And you can, in principle, I choose here a proper environment here that I want to use. I made the cloning of ISIS because then I decided to customize some stuff, and then it just works. Then it goes through some processing, so on and so forth. Here, doing some data calibration and ultimately a mosaic. And then things go on and on and on for the production of results, and again, sharing. All those notebooks, by all means, are somewhere here. So in our organization, and you have those notebooks here, and you also have other stuff. Those are some exemplary ones to download the data, calibrating data, for example, making a mosaic there, getting data from Zenodo. Those are some notebooks that I have been using, making the calibration and mosaicing from ISIS, so on and so forth, or using color ISIS. You have all that stuff there and more in our in the organization, right? And then yeah, then this thing about portability I said before. Yeah, and then as I also said, things that we have to do in the near future is one is to lower the footprint of memory. So there are some things I have been thinking about how to make those containers lighter. There is not much room here, but we should do that. I would like also to simplify even more the download of data for our users. And then we have some, I was talking to Pierre during this week. Maybe we want to move to use the authentication system that Vespa put in place with Edu team. And then I was talking to Pierre about some second layer or second tier verification that you do regarding groups and stuff like that to allow for. So this is one thing that we have to do, and that would, I guess, be a nice integration between at the service level. And maybe this is another thing that I have, and maybe we want to, I have discussed, started talking to Stefan also, if maybe we want to also integrate some the Europlanet membership in those systems, maybe something interesting to do. Whew. So this is for the Jupyter Hub. Do you have any question here before we go to the data portal? The data portal should be way lighter. For me, it's more boring because we talk, and maybe to everybody, because we talk about metadata mostly, but it's a important part of our infrastructure. Okay, so if we don't have more questions, or if we don't have any questions, let's jump in. We have 20 minutes, that's cool. So the data portal that we put in place, we went through, Riccardo said previously, I put that in infrastructure, in the context of infrastructure. What are we doing here? Why do we have this data portal? One reason is so we can have a place, especially when previously when the project was growing or making its first steps, we needed a place to put our data packages, so the geological, the geomorphological maps, and the ancillary data that we use for those maps. The thing, and then Angelo and I discussed about having like an aggregator of planetary data, an index of planetary data. Then we started developing this idea, which is something that it's going on. We started that, and we still have to develop. That would be for the last slide. We still have to develop some automation here, but this thing is going. We started doing that with Astropedia data products or Astropedia base maps. Also, it was important to be an easy to use data publication platform with some with some level of well, an opinionated data platform, but not that much. So we needed some formality here, some standard here. All right, so we, in the previous project in PlanMap, we had a homemade solution, and it worked fine, but it was very flexible. We didn't have validation process for that. So we are all human beings. We have moods or we have duties, and then the quality of the metadata may slip off the table. And so that was one thing that we had to improve in GMAP, right? Understanding that metadata, although as boring as it is, it's the way your data, it's the only, virtually the only way your data is found is through metadata, right? A good title. Everybody cares about a good title for their papers because that's metadata about your paper, right? A good format so that people can stick to the article, the journal standards, and so on and so forth. And we needed a sandbox to try those things. We know some of these data management systems or data or publication platforms. Probably Zenodo is the most known here in Europe. And to be very honest, that was the only one I knew when I started this data management argument. And as it happens, it's there are some out there, not many, but there are some, and this is growing steadily. So research data management is a super hot topic these days. As well, yeah, whenever we apply for funding and stuff like that, we have nowadays, it's mandatory that you guarantee that your data is going through some long-term persistent public/open data repository. So there are some/many, depending on your perspective, or sorry, depending on your area of expertise. There is none, though, for planetary data, for maybe obvious reasons. We are not a huge community. We don't deliver that much compared to, let's say, biology or health science and stuff like that. And the big players have developed, because they are here for, like Riccardo said before, USGS, they have their own solutions that they developed back in the years. They are these days, though, migrating to, as far as I know, one of the platforms. I know that USGS, for some of USGS, at least for Earth science, they are using Dataverse. The planetary crew, PDF, Astropedia, are going for CCAN, but everything is fairly new because of that. We have at most support for Earth, frame, but not some generic support for planetary bodies. Fine. So we got that. Then we have to make a choice, and our choice was to go with this one here called Invenio RDM, Invenio Research Data Management. That's what RDM stands for. And Invenio, there were different reasons why we chose Invenio. One, we can run on our premises. Two, it's a spin-off of Zenodo. So Invenio is virtually the same thing as Zenodo. I think actually these days they actually migrated behind the curtains Zenodo to use Invenio. I'm not sure about that, but that's in their roadmap. And they did that to provide to the community an open source solution and something that can run on your premises. It's it's in active development. For example, one of the things that they want to do in their roadmap is to federate the instances, so that every site, every university running Invenio, they can effectively link to each other in a network of data repositories, which is pretty cool. And one thing that was important on choosing Invenio, this is very fresh project. We saw this project grow steadily in the last 2 years. We started at version 5 or 6. I'm not. I think it was 6, and it's growing steadily. Now it's in version 12, although our instance stopped at version 9 because it's a lot of maintenance, and this is one of the lessons learned. When you get a project that is growing, and there is a lot of updates and things, migration of database and stuff like that. And I was naive respect on that. I thought that, yeah, I was optimistic, but fine. It's a great software by all means, but that's it. So we have one of the things that I have to do in the near future is to update and migrate the database to the latest version and stuff like that, but that's okay. Right. And one of the points there is that they use a fairly up-to-date and standard schema for metadata. So what are the metadata fields that we need to properly describe a publication? Believe it or not, there is a lot of research on that. And I kind of these days kind of like metadata because it's a whole world in itself. So there is this data site they put out. One of the things that they do, this organization, is to lay down a schema or a formal structure for metadata for different fields of science. Well, for all fields of science, let me put it that way. Right, so a general purpose metadata schema, which is which is one of the things about InVenue. So although we are talking about planetary, InVenue is a general purpose. As I said, there is no planetary data management system, and this is part of where the fun is, in the sense that how do you fit in and better? Now we are fitting in, as again, I'm just talking ahead of my presentation. Now we are fitting in, but how do we effectively develop that? Right, this is, and then this discussion can go on database and stuff like that. It's all made for Earth sciences, and we fit in somehow, and we have been doing that ever since. Right, so then we have, and as I said, we have our own metadata model. What are the fields that we need? What are the attributes that we need to properly describe our data products? So we are all used to title, authors, but then we have things like specific or frame-dependent, body-dependent information, right? CRS and the location in that body, so on and so forth, right? And then we also we also want to structure our data products in such a way that it's clear the synergy between the components. So we have this metadata model. This was inherited from the previous a project called GMAP. GMAP is built on top of that. It was slightly customized, and things go. It's science. We always inherit from that. This is again based on USGS long experience in managing planetary data, so on and so forth. We have this metadata model that we have to fit in InVenue, which is a general purpose platform. And then how do we fit in? So that, right? So that data side and metadata attributes and the standard is not broken yet, feels reasonable for the user to map. We call it the metadata mapping. So we have that. This is all documented in our wiki. Part of that is also in a GitHub repository because I have been trying to automate. So there is some brainstorming there too in that link that you see down below. I'm trying to automate this thing, which is one of the final points that I make in the future developments. How do we do that? Nowadays is a manual work. We instruct our users through the Zenodo interface. So you have the fields in there which are validated. based on data site, and then we say, okay, so the information about target, you want to put in this kind of descriptor. Output scale and this descriptor here, so on and so forth. And then we have instructions for all that stuff. So here then, how does that look? Well, by the way, our data portal is data.europlanet-gmap.eu as all of our services. You have a prefix, Jupyter, Jupyter.europlanet-gmap.eu, data.europlanet-gmap.eu. Here you have some links for some other resources, for example, the data analysis that I just talked about, our wiki, or a link for the search page where you can go there and search for the packages that we have been publishing. This has to load. Here there is a preview. Our internet, as we understood already, it's going a bit slow. That's one of the reasons why I have these slides here. So here are examples of our publications. Obviously, some pretty ones. And then we can go there. There is one thing that I don't like, for example, in Venue, but that's just the way it is. This code here in the URL, the record name. This is ugly, and I look forward to bypass that somehow. But anyhow, also because we in GMAP, and it was the case of PlanMap, we define names for our packages. This is one thing that we understand is very important, right? So you don't call a package simply SQT7Q whatever. You give it a meaningful name for the package, because we are talking about a package. It's not inside the package. You will find the map, the PDF, the documents, maybe the publication. We have a structure for that for our data package. Riccardo here is one of that helped to develop that internal structure of together with Angelo and others in our collaboration, and we give it a name. So there you find raster data, vector data, and we give it a name, a beautiful name with some codes regarding the target, right? Some abbreviation for the target. If it's Mars or Moon, then when you see the package name, you know more or less what's inside. You know it's talking about Moon, for example. You know it's talking about or it's talking about for example, here the Hokusai quadrangle in Mercury, and it's what kind of content it's in there. So this is one thing that we kind of lost with in Venue, and this is one of the points that is still there to be worked out, and we are. And then regarding the data index, we make use of, so it's time. We make, yes. So Angelo is just making a note for the online participants, what I said in my goals to whoever is willing to contribute. Go to the, for example, in the Docker repository that we have linked here in our presentation. Go there and just make issues. I can go through very quickly. Now I will wrap this up. Regarding the data index, then we don't have data inside our publication, but those are metadata only, which is a very nice feature by the way, of in-venue. So you can dedicate metadata only. This is how we do these days. There may be a better way, but that seems very logical. We use metadata only records to link to external resource. We don't want to republish, let's say, Astropedia maps. We don't want, that's duplication of data, plus it's their responsibility to keep that thing up to date and online. But we want to link, we want to, so when people come to our portal, they realize, oh, yeah, indeed, there is this base map using messenger data on Mercury. And I may look into that, and then you link that, and then there is the URL, some of the attributes there, we specify that in the mapping. This is where we link our resources. So the mapping is standardized also for us to kind of automate. So it helps us automate, not only gives the user a standard interface, but it allows for automation of reading those records. Right, so for the developments, as I said, we have to do here some, well, I did that most of the time. One of the things that we have to do, this is very important here, is to integrate or automate once the thing is published in our portal. If it's suitable for Vespa, then this thing should go to Vespa. So this is one thing that we have to do, and this is the most important point here. And also, as I said before, to create an interface and linking directly our Jupyter Hub to the data publication. This is something that it's being cooked. Actually, it's on the yeah, it's been cooked, and yeah, we are getting there. So just to, as I said, so in our repositories, we come there, you have, and should be appearing here. You come here, you open an issue with any feature that that you may feel like, and you just come here and say, I don't know, this thing is not working. And then you explain why is it working. I was expecting blue, but I got red, and try to give us some indication. Or I would like to have an interface for the data portal in Jupyter Hub, for example. Or I would like to have software X in the container. I don't know. It's very simple. And then obviously it's better you explain, but then we can communicate on that. This is a whole thread of stuff. You submit your issue, and then this thing, and then we can engage in
Thanks a lot, Carlos.
The discussion there. That's it. Thank you, everybody. Hope that was helpful.
Thanks, Carlos. That was very helpful. And of course, if anybody in presence or remotely wants to give a hand in testing, in documenting, please feel free, because of course, your help, I think, will be appreciated by someone else that is going to use this system, so an evolution of this system in the years and months to come. Thanks again, actually, to Carlos and Riccardo for the very nice introduction. You have all the materials available on the repo, and they will be linked. I believe also the presentations. We can reconvene in half an hour, and we have a bit more of a downstream thing. So what you can do with such tools, of course, using BaseMap to make maps, and we can talk in like 25 minutes in the next session. So another link, I suppose. Thanks everyone again.
Thank you, Angelo. Bye-bye. See you soon.
Okay.
Good morning again.
Angelo, yes, hello, are you there?
Yeah. Yes, I'm here, Riccardo.
Okay, it's about time to start, right?
Yeah, I think so. And also, as you may have announced, Ilaria cannot join, so she shared the link to a presentation, Ilaria Di Pietro from the Italian Space Agency. So we can actually refer to that. And of course, if you have any questions, just reach out to her, and she can share with you the presentation. And I think we can move on then with the program.
Yes. Okay, so this session is about mapping projects that were fostered and sustained by GMAP. As Angelo said, the first one couldn't make it, but she shared the presentation. And she's working at the Italian Space Agency. And now we have Beatrice Baschetti, who is a PhD student candidate at the University of Padua and INAF YAPS. And she's going to talk about the morphostratigraphic mapping of Mikumi crater in Meridiani Planum on Mars. In a second.
Okay, so yeah, this is a work I did on this small crater, which is located in northern Meridiani Planum, and is like the first step of a bigger project that I have and I want to do on the whole area. And so I will do first a briefly scientific introduction of why I'm studying the area of Meridiani Planum and what are my research interests. So we know that during the past, we have multiple evidence that Mars was probably warm and wet, like for example, the valley networks on the surface. But then, if we observe Mars today, is a completely different planet, which is dry, there's no water on the surface. And so when did this happen? So this change started to happen at the end of the Noachian epoch, so about 3.7 billion years ago. And so between the late Noachian and the early Hesperian, we had the beginning of this shift in the climate. And like I want to study specifically this shift, this period of the history of Mars. And to do that, I'm focusing my attention on the area of Meridiani Planum, which is a very interesting area with complex aqueous activity. And it's important that this aqueous activity spans both the Noachian and the Hesperian. So exactly, it dates back to this climate shift. And in this area, we have thick layers of sediments that are rich in clays and sulfates. So there's like the rocks here record multiple surface events which involve water, and that happen at this Noachian Hesperian boundary. And so the science objective of my study are to investigate how the surface environments change between the Noachian and Hesperian, and to reconstruct the characteristics of this transition in the area of Meridiani Planum. So I had to start from somewhere, so I started from this crater here. And this is a Mikumi crater. It's placed like in the northern part of Meridiani Planum. And here you have the opportunity landing site. And these are all different geological areas that are in Meridiani Planum. So this crater here has infilling of, why did I choose this crater? So it shows infilling of several hydrated minerals. And it's the crater floor has these layers of sediments which are clearly exposed. Like we can investigate the stratigraphy of these materials very well. And so for the mapping, I have used both CTX and high-rise images. This is, for example, a high-rise image. And then I've also used spectral data. In particular, there's these two hyperspectral cubes from CRISM, which cover part of this crater, like these parts. And then I have also used the digital elevation model from CTX. So this is the final result. This is a morphostratigraphic map, which I did using QGIS and Mappy. And I have put like all the units here and some surface features. And here's also a stratigraphic column of the sediments that fill this crater. And specifically, I have focused my attention on this area here, which has like it is where these layers are exposed. And so about the stratigraphy, this is a stratigraphic profile that I have extracted with the DTM and also using the map that I did. And you can see on both of these images, this is a 3D image of the crater with a CRISM image on top. And also this is this equivalent stratigraphic profile. That we have these layers of allosilicates here, and then a thick layers of sulfates. Actually, it's like about 100 of meters thick. And as you can see, this clay layer is on top of this thick sulfate sequence. And what is the scientific result of this mapping? So so this thing that we observe in Mikumi crater is that we have probably a drier and acidic period which favor the sulfate deposition, and then since we observed clay on top, we had a wetter period, probably at a more neutral pH, which is favor this clay deposition. And so that does not really follow like the transition from a wet environment to a dry environment. It goes on the opposite side. So it's actually, that might mean that we have more complex climatic conditions here at the Noachian-Hesperian boundary in this area. And it might imply that there was not really a sharp transition between these two, the warm and wet period and then the water limited period. Like probably we had this climate conditions that might have been oscillated a bit at the Noachian-Hesperian boundary. And thank you. That's it. Yeah, other questions?
You make the difference between your sulfate layer A and B. It is on the spectra or on the ground, but on the geography.
It's both spectral characteristic and from the stratigraphic profile. Yes, yes. I will show it in a second. If I can I have the slides back? Okay. Yes. Here, like yeah, you don't see this here, but on this image here, this magenta area, which is polyhydrated sulfates. And then there is this yellowish area here, this strip, which is monohydrated sulfate. So there is a spectral distinction between the sulfate layer. And also you can see on the stratic profile that the slope changes. So probably it's different layer with slightly different mechanical characteristics, like different erodibility, etc. So that's why we differentiated these two layers.
Okay, so thank you. Next speaker is Nicole Costa from the University of Padua, and she's also a PhD candidate, talking about a mapping of the northern polar cap on Mars. So please take the stage.
Thank you. Good morning to everyone. I am a PhD student at the University of Padua. And today I want to speak about the geostratigraphic map on the Northern Rupes, so again on Mars. But in this time we are on the North Polar Cap, precisely in this region. So the North Polar Cap is a flat dome, relatively young, made up by water ice, dry ice, and some basaltic dust. And we have the katabatic wind that erode the scarps and expose layers. And in particular, in this area, we have this North Rupes, which expose the upper part of the North Polar layer. We have an height of 500 meters, so it's quite high. And yeah, the exposed layer allow us to understand, to study the stratigraphy. So made the geological maps, and we can find in literature some example, mostly at regional scale, like these two examples. So we have a regional scale or at the entire polar cap. And another way to study the stratigraphy is thanks to the radargram, SHARAD. This is an example from Putzing et al. Is a nice example. And another interesting thing that you can find in literature is the correlation, the correlation between high resolution camera images like CTX and IRIS with the radargrams. And from this point, we start with our study. So we want to relate the composition seen on the surface thanks to optical instrument, and so study the stratigraphy and correlate them with the radar reflectors visible in the radargrams. The dataset is composed mostly by data from the Mars Reconnaissance Orbiter, and this is all the data set. So we have the the CTX image, the CRISM hyperspectral cube, and 2 IRIS images, and 4 equally spaced radargrams from SHARAD, and we use the MOLA DEM for the elevation data. And we start with the spectral analysis. We define on the spectral on the CRISM datum some units. We see some changes in albedo and geomorphological characteristics. And we decide after that to study this part, to concentrate our study in this part, so where the layers are exposed, and we select 5 regions of interest from which we extract the spectra. So here, and we can see that the first 2 spectra are characterized by the presence of absorption band of water ice, so these 2, while the other 3 spectra are characterized by not only by water ice, but also some features related to dry ice, so CO2 ice, and all the spectra show absorption band of fibering material, and clays. And we calculate also some absorption band, and we see that the layering is due to the variation in composition, and we want to extend these things in all the CRISM data. So we use we use the indexes proposed by Viviano and Beck, and thanks to them we produce this first color image, and we see where the different material are distributed in this area. The following step is the geological map, thanks to also GMAP and the tool Mappy. And we produce this map, so we mapped not only in the CRISM datum, but we extend also on CTX. And we define different units, so we can see a part of superficial unit. We have the water ice that is in this part, so in the upper part of the sequence related to the spectrum A. After that, we have this dusty water ice related to the spectrum B, and after that we have an alternation of a spectrum C, D, and E, which define the dry ice group. So we have an alternation of layer rich in pure dry ice and dusty dry ice. And after that we have in this region the Aeolian mantling that don't allow us to understand the stratigraphy below. And the other step is to extract the profile, the topographic profile along the shared footpaths, and create the cross section that we overlap to radograms. And the aim of this was to see if the geological contact between two units correspond to a variation in reflectance, and we see that we can correlate these two things. And so at the end, so in conclusion, we want to demonstrate that it is possible to relate the superficial variation in composition with the reflectance variation in visible in radograms. In fact, we produce this high resolution, high detail geostratigraphic map of a polar scarp, and we can see that on the top the layers are dominated by water ice. While we go deeper, we see an increase of dry ice and also dust material. And we see also that the variation in reflectance in the radograms are correlated with the change in composition. So I finish, and thank you for your attention.
Thank you, and very nice work. I mean, for me, it's the last time that I see such a detailed mapping on the layers of the polar layer deposits. So if you got any questions, this is the right time, or curiosities. If not, we will move to Yuqi Qian. I hope I'm saying correctly, from the University of Hong Kong. Ah, you are already on site. You have the ground truth for your map.
Oh yeah, thank you.
Okay, the stage is yours.
Yeah, thank you. So this is Yuqi Qian from the University of Hong Kong, and today I'm going to talk about the geological mapping of the Chang 5 sample return mission landing site. And this project is partially our European colleagues is funded by the GMAP or the Plan Map project. So today I'm going to talk about this here. The Chang'e mission, if you don't know, is China's first lunar sample return mission, launched in 2020, and it used two methods to take lunar samples, including a robotic arm and drill. In total, 1731 grams of lunar samples were taken by the Chang'e mission. And here is the pre-selected Chang'e landing region. Here is the Chang'e landing region. Here is other missions, and the red rectangle represent the pre-selected Chang'e landing region by the engineering team. And so pretty much my studying area focused on this red rectangle for most of my time before the landing of Chang'e. And here is the red rectangle, a more detailed. You can see that the western and eastern area of the Chang'e landing area are significantly different. For the western landing area, the craters are more larger and the crater densities are higher than the eastern area. And we can also see that their albedo are different here. The western area, or the western area, the albedo is higher than the eastern area. And this is because maybe, and here is the elevation map of the Chang'e landing region. We can see the eastern area is the western area is higher than the eastern area. This is because, maybe their composition and the units are different. So for a geological map, the first thing we needed to do is draw the geological boundaries. So based on our basic observations of the difference between the western area and the eastern area, and also based on the computation data, especially from Kakuya multiband imager data and climate data, as well as movement-logical mapper, the hyperspectral reflectance data. We subdivided 10 geological units in the Chang'e landing region, and you can see that the geological boundary of west area and eastern area are permanent, and the boundaries here, the western area is low, the eastern area is high. And for the computation methodology, they are also different. And after we get the boundaries, the next thing to do for typical geological map work is to know their geological ages. And we use a classic crater size frequency model measurement of different units and their ages. You can see that for the western area, the ages are older than the eastern area. So like the basic observations of crater densities and sizes in the case. And we know that the age of each unit. And for a geological map, we not only map the mere units, we also need to map other geological landforms. For the Chang'e landing region, we find like winkle ridges, volcanic domes, including basaltic ones and silica ones. The basaltic ones mainly distributed in the Mount Remoka. This is one of the three largest volcanic complexes on the moon. And the marine domes, they are also very famous because they are large and they are silica in composition. And in the eastern of the landing region, there is series called Rimash. And in the mare, there are some kipukas, there are some kipukas highlighted materials. When we combine everything together, we can produce a geological map of the Chang'e landing region. This is a small-scale map. The Chang'e landed here in the eastern part, and we can construct the geological history of the Chang'e landing region. And when the mission going on, I started the geological mapping of the Chang'e landing region like in 2016 or 2017. When the mission going on, Chang'e finally launched in 2020. We know much clearer the geological history and the scientific meanings of every unit in this area. And when the mission approaching, all Chinese scientists propose that the eastern part of the Chinese landing area is much more scientifically meaningful because its age, according to Harry Hissing's map, has an age of like several billion years ago formed, and it's actually lunar basaltic samples with such an age will never return before. Make it have lots of scientific meanings, like we can use it to calibrate, to constrain the lunar ecology function. That's the foundation of all created counting work of all planets in the inner solar system, and we can help that can help to constrain the lunar dynamo history. Not only it has more scientific meanings, it also is more easier and more safer to land. This is a risky map different of landing region produced by a leading scientist, Liu et al. You can see that the yellow circles are safer areas to land because there are lesser in the eastern of the of the pre-Slatic landing region. The eastern is actually more easier to land. The yellow circles are more. There are more yellow circles or safer areas in the east area. So my another geological map focusing on the Transfer landing site in more larger scale. So this is my working area between 42 to 44 degrees north latitude and 40 to 53 latitude west longitude. So Transfer finally landed nearly in the middle of my geology map. This map was completed before the landing of Chang 5, and you can see that for this area, it is actually not very complex because China goes there because it is a flat area, and it is also far away from highland regions. So it's very flat and simple area. And here is the composition data of the Chang 5 landing site. You can see that from different compositions, including titanium, iron, and other mineralogical data obtained by multi-band imager data, you can see that the Chang 5 landing site, the mere unit is pretty homogeneous. So we think that subdivide the mere units in 5 landing area is not necessary, but we do see some rays overlaying on the Chang 5 landing unit. On the Chang 5 landing site, we can see that those may be rays from distant craters, maybe hundreds of kilometers away. And for a larger scale map, we do need to map other things compared to the small scale map. And for the larger scale map, we map impact craters. And here is my classification different formed at different times. Copernicus craters, the rays are clear. Eurythenian age crater rays and rings are not very clear. I also mapped crater chains, crater clusters, etc. And there are also ghost craters, and there is a Kipuka here, and there is a Rima sharp, a Sinus Reyes. So there are different features. I mapped all of them, and we not only think about those features about the rays I just mentioned because they are permanent in the landing site. They may bring exotic materials to the landing site. So I also trace the rays of those ejecta source craters, and I produce a map of a crater ray. This can maybe help scientists to figure out where those exotic materials in the samples came from. And finally, after combining everything, I produce a larger scale map. And this map is partially funded by GMAP project to our European colleagues from Minster University. And geological maps can tell us a lot. So when I did a regional work and a more larger scale work, I can construct the geological history of this area. The basement is a PKT crust produced by maybe Imbrian impact, then erupted low titanium basalt. Because there is an age discrepancy between the Imbrian age basalt and the Eurythenian age basalt, there may be formed a Paleo regolith, and around 2 billion years ago, as indicated by the sample analysis, erupted the relative high titanium mirror source and formed the regolith layer at last. My presentation. Thanks for attention, and I'm happy to take any questions. Thank you.
Thank you. And
Yeah.
yeah, we have a bit of time for questions. If that's not the case, thank you very much for your presentation.
Thank you.
It's always good to see new maps coming out from Moon, Mars, and other planets.
Thank you.
Okay, so next part of this morning would be about a bit of tutorials of the tools we have developed within GMAP that are available to the community. So Carlos before showed an overarching view of the Jupyter hub. Now we will see the Mappy tool for geological mapping, the new CraterTool software for crater counting on QGIS, and also something related to 3D visualization of data by Giacomo Nodjoumi. So the first one would be me to explain about Mappy. See, can I sit there? So I have to connect this, right? Okay, so now we'll have to put our hands to make our hands dirty a bit with JS. So Mappy. Mappy is a tool that was developed by one of our colleagues, Luca Penaza, tested into the PlanMap project, and now implemented in the Europlanet GMAP infrastructure, and is also supported by and funded by the Jewish mission to the Jupyter icy moons. So what is the philosophy behind Mappy? So it's very easy. So when you build up a geological map, like for example, like this, you basically have your base map, your image base map, and it's overlaid by different vector polygons or line work or points that have different colors that represent the type of units with respect to their morphology or composition and their mutual relationship. And it has to be acceptable and published, whether it is for a geologic survey or for a scientific publication. It has to be topologically consistent. Every polygon has to share, for example, when a polygon and a unit is in contact to another, they have to share the same line, the same separation line, all the nodes or the vertices defining the line work has to be shared between a polygon and another. And if you have done some mapping with ArcGIS or QGIS, you have to draw polygons. Then if you want to make a change or an iteration, you have to move the polygon, then you have to snap the other one, and it's becoming a little frustrating. So we wanted to erase the frustration because we don't like to be frustrated. Time has a value, and we have to focus on the geology, not on the line work. So in line of principle, the philosophy behind Mappy is this. We try to approach this as we do on the field. When we do field work and we do mapping on the field, we have our topographic map, eventually our photos, we have the position with the GPS or just on the map, we understand where we are, and we go around and we mark the position of different units. When we see a transition between a type of rock and another one, we draw a line, okay? And this is what we do in Mappy. We just work with contacts between units and different types of rocks. That's it. So we only need to work with polylines. After that, Mappy is taking care of all the topologically consistency, the generation of polygons, the assignment of polygons to the specific geologic units. And how does it do that? We just need to roughly identify the separation between different type of geologic units. We don't have to be precise. You can do all these type of things, which are very nasty and ugly for a final map, but they are good for constructing a map. It's like, the philosophy is like drawing on a paper. You can take also your graphic tablet, you can draw your contacts, your line, you can make intersections here and there. And then Mappy generates automatically, recognizes the closed areas, like in this case, and puts a point entity inside the area, A, B, C, D. After that, the only thing the operator has to do is to give a name to A, give a name to B, give a name to C, and so on and so forth. And the name would be the geologic unit name. For example, I don't know, flood basalt, mare basalt, lunar highlands, equatorial layer deposits for Mars. And then Mappy automatically creates the stratigraphy, colors the polygon according to the unit definition name we gave, and also polishes the contacts. So you start from here, and with minimal interaction by the operator, you arrive to this result, topologically consistent, with all the stratigraphy already placed in the correct position, and all the dangles and this kind of ugly line work deleted completely. So it's fairly easy in line of principle. How to do that? So this map was constructed by Mappy. You see there is a line work, linear features like flow channels, fractures. We have the stratigraphy of the map here. Yeah. We have some contacts here and there, and then we have some base maps here that I don't want to mention now because this is not the topic of our talk. And here you see we have a point shapefile. If I enable it, maybe I will increase a bit the size. You will see that they are exactly what I mean. So these points are within closed areas, like one for the central peak of the crater, this other one for the other enclosed area of the central peak, etc. These are the ones we need to interact with to create the geologic units. And now, in the next like 5 minutes, I will demo how to do this and how to use Mappy. So let's say that we start with the same base map we have. I will do this. I will remove this group. So Mappy is a plugin that is already in the plugin manager of QGIS. Okay, so you just need here to go to plugins, manage and install plugins. You got your plugin manager. The only thing you need to take care of, and by the way, everything I'm saying here is we teach it every year at the winter school, and if you go to the GMAP winter school website, all the recorded lessons are there, so this tutorial is available to you anytime. You have to go to settings and flag the show also experimental plugin. This is classified as an experimental plugin by QGIS. This is the only thing you need to take care of. Then you can type Mappy, and this is the only result. You get a brief description. You will get more information. For example, you can jump to the homepage of the plugin. You can click install experimental plugin. I have already installed, but it's here. And once it's installed, Mappy creates two buttons, which are these two. Yeah, these are the only commands of Mappy. This gear icon and this reload or refresh icon, recompute map, it's called. And then if you don't have this sidebar here, you can go to processing toolbox, and this is the processing toolbox of QGIS, standard one. But once you install Mappy, here you have also another menu voice with different type of options. And so Mappy is doing a nice thing. It's not only creating a good line work or good polygon for your map, but it's also creating the mapping project for you. It's also automatically downloading the planetary geological symbology for you, and also other small functions. So let's say we have loaded our maps here. And the first thing I want to do is to go here to mapping and double click this option. This is called auto download and setup mapping symbology. This is pulling a custom made geologic mapping symbology according to the USGS standards, and it's installing it in your computer. Once you did it the first time, you don't have to take care of it anymore. If you click run, it's pulling this information, installing it in your computer. If you want, you can also have a look at the repository in GitHub if you are curious, but this is how it does. And I mean, this now the network is not super responsive, but now, if everything goes well, this should not complain. Let's see if it works. Okay, if it doesn't, I can cancel it. Or I can close it and we can move forward. This is running in the background here. Next thing one can do is the quick mapping project setup. So let's say you just open a mapping project, you throw in a bunch of base maps, then you double click this. And this is basically creating the QGIS project for you with the proper map projection. For example, this is the template we have that was pulled in reading the coordinate reference system of the raster base maps. And this is where it's asking me to save it. Let's say I want to save it here. It's prompting you a default folder in your computer, but one can create his own folder. And to do that, you have to go here and you can save to directory. And for example, I want to create a ERIM directory. And inside here, if I click open, it's creating a mapping project. This is Copernicus crater, so we can call it Copernicus map. And here you have another flag, which is very, very, very important. It says create an additional line layer for structural mapping or linear features. You will see in a moment what it does. Okay, so if I click run, this is what it did. We have our project here above, is called Copernicus map. It created here three different files: source indicators, source contacts, and linear features. These are your main files that you have to work with Mappy. Here we can just collapse all these things. We don't really need them. These are the files you have to work with. And the project is saved here in ERIM. Copernicus map, it's created a folder. Inside the folder, it's created the project file, and all these vectors are saved in a geo package, which is a box. And inside it has these three files, which is a point shape file called source indicators, and two polylines. One is called source contacts, and the other one is called linear features. So what are they? Source contacts are the very first thing you need to work with, and they are the line work. This, yeah? Source indicators are the points that are naming your geologic units, and linear features are just any linear feature you have, like a ridge, a fault, or linear elements that do not need to be outlined by a polygon. So when you do mapping, the first thing you want to do is to work with the source contacts. But before that, you see that I have a menu here. This is a menu, a contextual menu of Mappy. Basically, this is the gear button. Here it says, I am working in this mapping project, which is the one I just created. My limits layer, so the contacts between the units, are the source contacts, which is correct, and the indicator points, so the names of the units are the source indicators. The unit name is the attribute table field we have inside the source indicators. You just have to check that these are in this configuration. You don't have to see this menu anymore. Just open it once, because if you have our other shape files, our other vector files, it can sometimes read other things. So click on this icon, gear icon, have a look that you have a limits layer, source contacts, indicator points, source indicators, and unit field is unit name. Once this is verified, you can close it and you can forget about it. Okay. If you close your mapping project, you have a lot of other lines and points, and you reopen it, maybe it's a good idea to check from time to time, especially once you close QGIS and then reopen it. So after this, we can start to do our line work. I can just double click and change the symbology just to make it more visible. I can make it red and a bit larger, like 0.8, so we see it. So now, for example, we have this beautiful crater. We have it's outlined by a very sharp rim all around, and we have the central peak, which is very prominent and very well visible. Okay. Let me just enable the visible imagery, for example, this, which is much nicer. So let's say we want to outline the central peak. Now these layers, I have put them just for completeness. And if you log in into the Winter School website, you can download all these layers for this exercise. But we can also use this. We want to outline the central peak, which is a big chunk of material here and another one here. To do that, we have to select our source contacts, go to our pencil, and then you have various options. For example, this is to create a new polyline. And then I have to can zoom in. I have this, the cursor is becoming a crosshair, and I simply can add nodes outlining this feature. Now I'm doing it very, very badly, so please don't judge my mapping quality, because I know, this is why I'm telling you. The only thing you need to take care of, and really this is the only thing, please do not leave it open. If you leave this open, like if you end up your line work here or here, Mappy doesn't recognize the closed areas. The best way to do it is simply to cross the tip of the two lines. And once you add a new node beyond this line, a green cross appears. Then you right click with the mouse button and you are prompted with the window. The window is just asking you, what type of contact did you map? How certain you are? You are certain, you are interpreting, you are inferring. At the moment I can type certain. And this is now becoming permanent, at least for the moment. And then I can add, for example, another one here, yeah, outlining this central peak portion here below. There are also ways to digitize like continuously with a graphic tablet, but this is not the scope of the tutorial. So again, here I can make this thing, green cross, right click, certain. Okay. Now, we have also the interior of the crater. We can mark it very roughly. Yeah. Whoop. Let's zoom in and then let's cross it. This is again certain. Okay. So you see we are constructing just the boundaries between different objects. And now we see another nice thing, especially from the DTM. This portion here is much, much smoother than this other portion, but the separation between the two is a bit subdued. You don't really see where it is. You see it is roughly here, going here, and then here. So one can do something like this. You can start marking it, more or less it's passing through here, maybe going here, and here again, but it's not a very clear separation, yeah? So in this case, one can say inferred, yeah? And these are important because they will be symbolized later on by Mappy. Okay, we can mark the outline of the crater here. I think this is the ugliest map I ever did, but this is again very much certain. But we have again another uncertain thing. We have the proximal ejecta. You can barely see where they are, but it's not a very sharp contact. So we can interpret where the proximal ejecta of this crater are, more or less. Yeah, like that. And these again are inferred. Okay, let's say we have outlined some nice things here at the crater. So now what? This is basically what we need to do. The only other thing we need to do is to hit this button. And you will see, I will take these source indicators first, and I will move them just above the source contacts. Now you will see why. When I hit this button, many things will happen. The first thing that's happening, our project is saved. Okay, everything we did is saved. So it automatically saves your line work if you forget about it. It's saving your project just in case. And then is calculating all the closed areas, transforming them into polygons, and placing a point inside the polygons. Look at it. And now you will see also something more appearing here. It's asking you, do you want me to save your line work? Yes, please save. Okay. So something happened. We have a final map polygon layer. Now it's null because it's all the same stuff. We need to give a name to the different units. We have another thing appearing, which is final contacts. And I will show you that here, you see this ugly thing? This is the source contacts, but the final contacts are clean. You don't have these ugly things that are just for constructing the map. They are your construction lines. But now they are polished and made as a beautiful line work outlining your polygons. So the only thing we need to do now is to use these source indicators as a name for the different units. So let me just make this a bit transparent so we can at least see what we are working it. And by the way, if you want to have a transparency interactive slide bar here, you go to legend in the properties, opacity slider, you enable it with this arrow, you hit apply, and then you can have this very handy. So here, for example, we have, I don't know, proximal ejecta. We have this point. So we select our source indicators that is in the attribute table like that at the moment. So you just have an ID number, progressive from 1 to whatever, and the unit name. If you select the one you're interested in, for example, this one, and you go to the attribute table, this is the proximal ejecta. So I have to enable the editing. You see that the pen icon is placed anywhere in the system, so you can easily access to the editing capabilities. And here we can write proximal ejecta. Yeah. Then number 5. Let's select it from the table. It's becoming yellow. It's this one. This is inner slope or inner rim, inner slope. Okay. Number 4 is this one. This is a hammocky material. Hammocky material. Number 3 is smooth material or impact melt, for example, could be impact melt. And then we have number 2, which is this portion of the central peak. And number 1 is this portion of the central peak. So if they are the same type of thing, you have to give the same name. For example, central peak, if you have to be consistent with the names. If you give different names, you will get different symbology out of it. If you give the same name, they will be categorized as the same unit. It's very, very intuitive in the end. Once we have done this, we have basically created our legend and our stratigraphy. The only thing we need to do is to hit refresh. It's asking me, you want to save because we have modified the source indicators. Yes, save. And now we have our stratigraphy named correctly as we told the system to do, and the map is symbolized with the different units with different colors. You see that the 2 central peaks, since we gave the same name, are now the same entity. And the only other thing that you need to do, if this is placed in the incorrect order, you have to go to the symbology here. And for example, we can put the central peak below, which is you have your stratigraphy placed correctly. And now what? Now you can continue to work on your map. You can improve your mapping. For example, now we have just constructed more and more lines. If I want to mark, for example, small impact craters, I can work with source contacts here. I can disable for the moment the final contacts. And I can add, for example, an impact crater here, like a small one here. And I don't know, just maybe another one here. Okay, so now if we refresh our map, this will be populated with points and they are becoming a polygon. You see, now they are becoming a polygon. It's colored in orange because it's null. We didn't give the name yet to these 2 entities. So we just need to select this and this point, give them a name. You will see null and null. So source indicators, we go to the attribute table, we name them small crater. And then also the other one, which is the same thing, is small. Okay, now we refresh the map and they are becoming small craters, yeah? And then you can go in the properties and you can move up and down to create your own stratigraphy. Once you're happy, you can disable your source indicators, enable the final contacts, and disable the source contacts, and you will get your polished map. The nice thing to have is also the, and it's the best part of it. If you want to refine something or improve something, you don't have to work on the polygons. You only have to work with your source contacts again. So let's say that we want to move a bit the border. For example, here I have put the inner mare unit, inner impact melt unit a bit too far. I want to make it like here, pass through here. What I need to do is to select source contact, be sure that I am editing it, and then close to this button we have this other button which is to modify things. If you hover your mouse above your polyline, you can either move the vertices like that, or you can translate the line work. So there are many options. You can add more nodes, for example, like I'm doing here. If you click on the central part of the segment, you will get a red cross appearing, which is adding a new node. So I am moving a bunch of stuff now. Our old units are here, but I want them to pass through here. So once I did this, I just hit refresh, I save, and now this is improved. So you see how easily you can improve iteratively your map. So I want also to improve this contact between the slope terraces and the inner slope of the crater. This is very much convenient. You can do this and you can refine your map pretty easily. So with this system, you just need to take care about contacts. Everything else is taken care by the software. The last thing one can do eventually is to symbolize the source contacts. If you go here, actually, if you go in the attribute table, you remember that I said certain, uncertain, interpreted, etc. If you open the attribute table, you see that they are uncertain, inferred, etc. Sì, Angelo, sto sforando, vero? I'm just finishing. So one can do one thing. You can double click, you can go to categorize symbology by certainty, you classify it, and then, for example, you can choose your planetary symbology, like this is a certain contact, this is an inferred contact, so maybe it's dashed. You can click apply, and once you refresh your map with Mappy, also the symbology is applied. So once you have your final maps and your final contacts, you will get a dashed line here because this is interpreted and not very clear, and all the other ones are placed as certain contacts. So this is the principle behind Mappy. Very quick tutorial, and I'm sorry if I stole time to other people, but then you have like a fresh view on everything else. And if you want more details, you can email me, or you can join our monthly calls, or see the recorded videos for the winter school, or join the winter school. Thank you. Next. So next one would be Thomas. Sorry, Thomas. Where is Thomas? He's online? Okay. Sorry, Thomas, to have stolen a bit of time. And he's going to talk about the OpenCraterTools.
Okay, all right. So thanks for the opportunity. And today I want to talk about our OpenCraterTool, an open source tool to determine and compare crater size frequency measurements. As you know, accurate measurements of crater sizes are essential for dating surfaces. And with the rising amount of new high-resolution images in recent years, various regional and global data sets have been created. But if you have a look on the crater sets, you see a lot of difference, so it might be a good idea if you count them by yourself. In 2011, Kneissl et al. Introduced a map projection-independent crater counting method that was implemented in the crater tools for ArcGIS, where users were able to count craters on any map projected images. In the background, different map projects were used to take advantage of the advantages of the projections like equidistance or equal area. However, the Crater Tools is outdated, and then we decided to have a new updated version for QGIS. So the OpenCraterTool is a free and open source plugin for QGIS. So no commercial license is required. It's available for Windows, Unix, and Mac OS, and it's written in Python. So if you have a look on the code, you can have a look what is happening there. Our tool enables a map projection independent measurement of craters. You can install the tool from the plugin repository from QGIS. Just go to plugins, manage and install plugins, and then you search for the tool, click on installing, and then you have it on in your browser. Then you see the circles, and you can use it. You can alternatively install it from GitHub, and there's a detailed installation guide on GitHub. What you need for crater counting is 2 layers. You can create these with our create shapefile tool. First is the area layer, where it has the area name. You can define it by yourself. You just map your area, and then the tool calculates the area size. And in the crater layer, you have the diameter in kilometer and the coordinates of the center. Then you can start identifying the craters with the 2-point tool or the 3-point tool. You click on the point on the rim, and then you span out we call a rubber band, so you can exactly size the crater here. What happens in the background is that we calculate, the tool calculates the center of the crater, and based on the center, we're using an azimuthal equidistant projection with the crater center as the projection center. Then we build a circle with using 300 vertices, and all these vertices have now the same distance to the center. So this is a representation of almost a perfect circle. And we calculate the diameter. And since the tool is open source, you can go into the code and edit these 300 and make it to 600 if you want to have a better quality representation of your circle. And the calculated diameter is saved in the circle object, and then the circle object is reprojected to the user-defined projection and saved in the shapefile. With our preview plot tool, you can have a quick preview of your measurements. Here, all the craters are shown in a logarithmic cumulative plot. And you can decide if you want to show the fractions of all intersecting craters or all craters with the centers in the area. And here you see the bin version. This is an interactive plot, so you can click on a bin, and then you see all the craters within this bin highlighted on the map. You can, of course, export and import your measurements for a detailed analysis in crater stats, or if you want to have nice plots there. You can export this as a diameter file or a spatial crater count file. And of course, you can import these files to rebuild your shapefiles. This is completely compatible with the ArcGIS crater tool, so you can use old files as well. We have also a grid tool that supports the crater counting processes. This is based on the measurement area, the map projection, and the user-defined grid spacing. And you see here that the grid relies on the area you defined. What we also have is a crater comparison tool. This allows a quantified comparison of 2 crater measurements. For example, here it's just ideas if you have a gray crater count and a blue crater count, if you want to compare them. The first step is to match the craters that represent the actual crater on the surface. And for that, we need some thresholds. And we decided a good threshold is, for example, the diameter ratio between 0.5 and 2, so that the craters have almost the same size and that the distance between the crater centers is not too big. So here you see examples of good matching craters. They are really good. And here's a boundary example. They have a ratio of 2, so this will count still as a matching crater. Here we have examples of non-matching craters. Here the size difference between the craters is too big, so these will be separate craters then. Here on the bottom, you have another example of here. The sizes are the same, but the distance between the craters is too big. So this will be two separate craters in the matching. The second step is the calculation of the statistics. We calculate the number of matching craters, the number of over and under counts, and based on the matched craters, we calculate the ratio, the absolute and relative mean differences of the crater diameters. And here is how does it look like. You open the compared count tool, you select your crater counts that you want to compare, then you click on plot, and what you see is the matching, the reference diameter plotted on, and then the ratio. And the black boxes, this is the bin data, and the gray circles represent each crater pairs that were matched. And if you click on a crater pair, you see then it zooms to the actual craters. You can also export the statistics for further analysis if you want to calculate your own statistics in MATLAB, or if you want to have nice plots there. We used our tool to compare 5 global loaner catalogs. 3 were based on manual counting and 2 machine learned products. And here on the right side, you see the issues or the differences we see between these catalogs. For example, in A, we see different definitions of the crater rim of the basins. So some counted just the inner one, some counted both, some counted just the outer one. And here you see how the catalogs handle secondary craters. Some include them, some not. Then in C, you see overcounting and undercounting in samples. And on D, you see your more complex situation. If you have intersecting craters, some here see just one crater, others are 2. So we analyzed all craters with diameters greater than 5 kilometers. And the comparison revealed substantial differences in both the number of craters and the crater diameters. So the number of craters varies up to a factor of 3. And the diameters, overall, the mean values are good. They are between 0.4 and 2.5%. But if you then have a closer look and you see many outliers and maybe many over and under counts. So in conclusion, our tool is an open source tool to map for map projection independent measurements of craters. It also allows a quantified comparison of crater measurements, and our comparison of the lunar catalogs revealed substantial differences. For a detailed description, have a look on our paper. And with that, I want to thank you for your attention, and I'm happy for questions and suggestions.
Thank you, Thomas. And I think this is really a very important step forward and improvement. We were dreaming of having this in Python and QGIS since years. So thank you. And any questions about it? Okay, if that's not the case, thank you again. And we will have Giacomo Nodjoumi from the Constructor University Bremen talking about radar visualization analysis tools that he developed for the Explore ACA 2020, that you see the banner just there on the left of the screen. Giacomo?
Thanks. Hello, everyone. I will share my screen. So I will try to be brief because this is a lot to explain. But so if you have any question, if you want further details, please reach us or reach me in GMAP, Discord, whatever it is, by email. So I've started to work with radar data from 2020, more or less, and I've tried to create something that can be used to reprocess the data that I'm working on, but also others that want to work with data can use this tool to work on it, especially for reproducibility of the tools, of the results. And especially since there is kind of a lack of an overall tool that can be used to do the whole pipeline, from download the data to process the data and then export in more advanced format or in advanced visualization. More or less, the radar analysis start with the download of the data, and we can do this, for example, using the normal data archive from PDS, but also we can use REST API that are a newer and kind of cooler way to download the data because you can directly query the data archive to retrieve your desired data. And for this, Carlos, that is there right now, developed this geoprocessing tool, GPT, in which you can use to access the data remotely just by passing some variables. So I tried to implement this into a Jupyter notebook. And then, for example, here you can see that I'm querying the database to retrieve charade data from the MRO orbiter. Then I get all the possible data that I can download. And then I specify a bounding box. And then all the tool will just simply, if it runs without problems, yes, it will generate my data archive or data results with all the data that I've downloaded. And it can show me where I'm looking at. So the bounding box that I've searched, this one, and the footprints of the data itself. Now the backend is kind of slow and this doesn't loading the base map, but then you can see that, okay, all the data are in within or crossing the bounding box, but maybe I don't want to download them all. I just needed to know how many data are there. So I can use those selection tools. And then, for example, okay, I want to download all of those, only those. And maybe, I don't know, another one here. Oops, too many, too many. Oh, sorry, okay. There are some bugs, still some bugs. But then I can just simply continue the code. And then it will retrieve only the data that I wanted to. Now will compute if I have already downloaded the data, then it will retrieve all the links that I need to properly download those data. And it will download if I specified some, if I set some specific flags, also the simulation from the USGS radar team, charade team, and from the Italian data team. Because those are not in the same data archive, or at least are kind of different in the same data archive. I have different paths. So doing this, then running this, I will not do right now because it will take a while to download all of those data. It will download the original data, TIFF processed image or PNG image processed by the US team or the Italian team, then the simulation, and then ancillary file from that is generated within the simulation itself, which includes all the simulation parameters like the nadir returns, the off-nadir returns, and a lot more data. Then we can move from this download folder, download notebooks, to the proper processing notebooks. Now it's focused on charade, but actually it's compatible with slightly adjustment with the MARSIS and also charade Italian radar tracks that are processed in a slightly different way. So just to be brief, this is almost automatically. You can just run this. Well, actually, you have to specify the path of your data. If you have a bounding box, or if you want to show bounding box derived from an image, for example, here I have a CTX, and then just run it, and then it will open a new window in which there is a drop-down menu which contains all the list of all the data that you have downloaded. And then this is the interface. So you're looking at the base map that is retrieved from a WCS service automatically and download into your folder. So everything that you are downloading here or processing here will be also stored locally, so you can access them in GIS software, ArcGIS, QGIS, whatever it is, because the maps are in GeoTIFF format while the vectorial data are in GeoPackages. So everything vectorial or GIS compatible. So here we are looking at the bounding box, the footprint of the radar track, which is now the this one. And I can zoom in, zoom out. And of course, it will load only the base map that is covered by, or at least that centered around the footprint. So it will not download extra data. But you can add eventually if you want to show additional data, like the whole context of the area, you can add it. It's not a problem. You just need to implement those additional functions. Then you can see the main plots. On the right, there are the original data, so original acquisition data, original simulation data, and then on the left, you have pre-processed data, which I applied some pre-processing to enhance the data. But it is used, I can show you, for example, here, you can see that those, okay, now are covered by my manual picking, but actually those are clearly more visible. Those reflections in the subsurface are more visible into the pre-processed image rather than the original data. And of course, the workflow implies that you have to compare the actual data that has been acquired by the instrument, Baschetti, with the clutter simulation to see if your reflections are actually clutter. Clutter are simply echoes in the subsurface, but that are caused by surface features that are within the lobe of the radar. So, for example, if we look at here in this image, I will actually we can go there because one thing to mention is that all of those plots, actually there are more plots, are synchronized. So whenever you zoom in one of the plots, you will have in the other like this gray area, which shows you exactly what you're looking at in the image. So if I zoom in, zoom more in, zoom more and more, just to be here, I can change the scale. So for example, here, here. We can see that in the radargrams, the acquired radargrams, there are subsurface reflections. But actually, those subsurface reflections, if you go into the cluttergram, clutter simulation, are actually the clutter simulation, are actually clutter that are caused precisely by the presence of this rim of this crater that is sending back echoes fast, or at least earlier than the actual surface. And in fact, those purple and cyan lines correspond to the first returns and nadir returns, if I remember well, or is the opposite? No, this is nadir returns and first returns. So having everything together helps a lot into the picking phase. The picking phase is properly the design or the draws of your subsurfaces. Usually this is performed by looking at the radargrams, looking at the clutter simulation. So if we can go back here, and also looking at the vertical profiles of those echoes. So for example, here on the right, here, we can see both the vertical profile, the vertical slices where those crosses are, sorry, in which the blue line is the the clutter vertical profile, and the red line is the radargram vertical profile. And so you can see that you can do exactly, you can select precisely where to put your picking, because you can do, for example, with this one, you can activate, you can edit points of some reflection that you did in the past, or you can just simply add the new one, and then you can save, and then it will automatically compute the maximum profile, or at least the maximum picking, the actual picking by looking at the maximum values in a range around these simpler draws, and then it will create a more complex and refined picking like this one. But you also have to check about the radar backscatter data. So for example, here we can see that we are looking in this phase. So sometimes you can see some subsurface reflections that are actually not subsurface reflections, but are echoes from the surface that are just going underneath. And you can see that when looking at the backscattering power, and if there is a huge discrepancy between those two lines, which are the backscattering power of the surface from the surface, from the clutter simulation and the radargram, maybe there is some problems. And also, you usually need to look at the DEM profiles. For example, this is MOLA. And of course, the better the DEM it is, better accuracy you can achieve. Of course, here I cannot achieve a great accuracy, but since I'm looking at the tracks that is more than 100 kilometers, them that has 200 meters per pixel resolution, is okay. And then you can see that the NADIRC registered mola, so the green line, is pretty much accurate with the mola. So, okay, for this analysis. So my subsurfaces are kind of valid, can be defined as valid. So I can do this picking for this track, then I can save this track, I can switch to another track and repeat. Then what I wanted to do, or at least usually, the analysis stop there. You can further process these slices by computing the loss tangent, the attenuancy of the signals, the roughness of the terrain, but all bidimensional analysis. What is really interesting, and is only performed in few locations, or for example at the poles, thanks to Putzig et al., that produce really amazing 3D models, or in other locations, but they used proprietary softwares like Sizeware or others from Earth seismic data analysis. But it's really useful to move from a bidimensional space to a three-dimensional space, especially if you have very near tracks, because you can have a spatial correlation that will further approve or actually not approve, but validate your picking, or else it will maybe unvalidate your picking. Because if you have a consistent returns or picking of the same subsurface across several tracks that are distanced by 100 meters, 1 kilometers, maybe those two layers may be exactly the same or belong to the same surface. And so after collecting all of this data, everything will be saved in a data frame, or especially in a HDF file, which can be run or open with a with the second notebook, which is everything. It will be published. Now it's still non-published because I need to fix some bugs, and then it will be everything published within GMAP. And here I can see the surface, the automated retrieved surface returns, and also my picking. Of course, this is still in time domain, but now since we now have all the data, we can convert into a space domain, so we can retrieve the depth. But then maybe if looking at those in a three-dimensional space, since we can move around, we can see some, for example, consistency along different tracks. For example, I can see that those tracks seems to be or seems to belong to the same surface or subsurface. So what about we can do some grouping, and then we can visualize only the groups that I created, and just simply assigning to a specific subsurface ID a group, and then I can see only my group. So okay, maybe those belongs actually they're real. They're probably the same surface, or actually maybe this is not only a surface but a closed surface. But also in general, you can do this for several tracks and repeat the process, and then you can create a mesh. Having a mesh give you the possibility to see better what are those subsurfaces that you are mapping or trying to map. For example, here I computed the meshes from the surface, and then I can compare this with the digital elevation model to see if, for example, I have a lot of discrepancies, or this can be validated by the DM analysis. And also I have the subsurface that in this case actually are closed surface because the algorithm that I use to create those meshes doesn't, it's kind of a convex hull creates, so it will close the surfaces. But actually you can create non-closed surfaces, and then you can compute volumes, areas, perimeters, and so on when converted into the space domain. But also if you, for example, if I decide to close those two subsurfaces, I can create a real closed surface, and then I can compute volumes. But also, since those can create also, or can be converted into a DEM, we can extract some morphometry parameters like directionalities or topographical index and so on. So just to conclude, the whole tool is kind of cycle tool in which you can start from the download of the data. Start from the download of the data, then move to the analysis notebook, do the all the picking, then move into a 3D space analysis. Then here also, if you look at, you see that there are some problems. For example, okay, no, probably here I assigned this group wrong, or I picked this very bad. Okay, you can reload the same data into the original notebook, and then you can edit and redo your picking. And then you can save it again and move again to the 3D space and back. So it's kind of a back and forth analysis. And then at the end, you can export that meshes into DM, a lot of other stuff. So that's pretty much it about this tool. I hope that it was not too much to be condensed in 20 minutes, more or less. So if you have any question with this, oops, this one.
Thanks, Giacomo. And it's very nice to see that we are wrapping things around these radar data sets that look like black magic to some people. So this is really useful and helpful to visualize them in 3D. I saw that there is a raised hand, maybe by Angelo. No, video. Any other question in the meantime? I know it looks intimidating with this amount of code, but in the end, it's not that difficult.
Exactly.
In any case, one can contact Giacomo and can give you tutorials. By the way, we are trying to see whether to make a workshop of 2.5 days or 1 day within the winter school or even before to just get your hands dirty on this.
Yeah, exactly. So the idea is that probably we can try to arrange some smaller scale workshop in between the scale of this and the winter school that can be then shared. So we will keep you posted later in summer, but definitely at the winter school we will touch these topics. And actually, thanks a lot for the patience also to stay a bit longer than the dedicated slot.
Yeah, and then if we still have time, I'd like to share also something about, in like 5 minutes, the work with the Explore project. So within the Explore project, we are developing those two lunar SDAs. One is focused on the regional scale map analysis or production of high-level images, like from hyperspectral cubes, filtered hyperspectral cubes, and more, but also 3D models from the DEMs and more. And then there is the LX that is more focused on a landing scale. So this will be more focused on the production of the 3D models from, for example, Apollo images, and also to implement some spectral analysis tool and more, involving also machine learning, the machine learning team and machine learning pipelines. So just briefly, this is the platform. This is the main front end of the Explore platform, the Explore SDAs. Simply the moon now is rendering a bit low because there are some connection issue also with the sharing, so I had to reduce a bit the quality, but you see here. But then you can switch from the global DM or global WAC, and then you can simply connect with already available backend like the USGS Lunar server, but also with our backend, which at the moment is not ready reach because it's still in testing phase. But for example, we have kind of some test data set, like can just add some data and where it is, contour lines, both raster and vectors. Also this one, and there is this one. So then you can zoom in, and then you can see all of those in a mess, but it's kind of in a GIS-way style, in which you have all the layers. You can arrange those layers, and then you can navigate in a 3D space. You can zoom in, zoom out. Of course, a lot of functions are still need still to be implemented. But at the moment, for example, we are seeing contour lines. That is a simple shape file that can be computed also dynamically using the backend. But also we can see, so this is the control line, the NAC image, so the highest resolution available. shaped on the 3D terrain derived from the LoLa. And then also, for example, we can have the Clementine image projecting into the same area, and so on. But then you can also use a split screen to see, for example, both images in the same time. Well, actually, with this, it's not really worth it, but maybe with an FX spectral data could be worth it. So right, no, sorry. Right, and this one left. So actually, okay, one layer is not loading. Okay. No, this is Valentine. Sorry, I pick up the wrong layer. Of course, all of those names are still temporary. Architas, here it is. So for example, this is an RGB composite from the MCube data. And you can see, for example, here you can both overlay the data or have a split share screen to see both of them in a kind of fancier way. But also you can have a pedestrian mode like the Google Street View. This is mostly for the human scale exploration when the all the 3D models will be released and deployed, and then you can navigate, you can turn around. Of course, here you will see all the huge pixel from the MCube and Clementine, but once you have the highest resolution possible, you can have probably better details, and so on. But also, I wanted to show you what is the shapefile. Some pipelines which are based on the processing of spectral cubes. So we have developed this spectral profiler that at the moment is still in testing phase. We are implementing more features like spectral band comparison, comparison, and so on. But with this tool, you can simply just click on your, for example, I can activate again this one, and then it should visualize this. No, this is okay, this one. And then, for example, I want to pick only some pixels, and then I can download this into a CSV to plot with Excel or implement in other workflow and so on. We have also spectral band composition pipeline, but at the moment is deactivated. We have some issues in the backend, but as soon as it will be published finally, it will be with this. It will be possible to generate those RGB, simple RGB composite, but also some spectral spectral indexes. Which for this I will leave the speak to Javier if he wants to join, because he's focusing on the creation of those spectral indexes from the MCubes, and with the open source pipeline that will also be available within the GMAP project. So yeah, I stop my share the screen. And of course, if you still have some questions, just join us on GMAP Discord or write me an email or whatever. I'll be happy to answer your questions.
Thanks, Giacomo.
Thank you, Giacomo. Well, I will try to be really quick, so maybe 5 minutes. So this is actually a showcase of 2 of the tools that we are developing in Constructor University. So in here, I am using the Jupyter Hub that was presented by Carlos this morning. And I will also show you some things that we will upload in the Explore, but in our platform of Explore that Giacomo was just showcasing. So as Giacomo said, basically the idea of this tool is that we have an open source way to generate spectral indexes for MCube. Basically, this idea comes because it's not that easy to access this kind of data. You usually have to use proprietary software like IDL. So we replicated different indexes and different ways of filter the MCube data. So it can be open, can be accessibly openly for everyone and in Python. So I will not run any part of the code because it will take a lot of time, but I just want to showcase one of the things that we expect to contribute with this workflow. So one of the main characteristics of the data cubes of NCube is that we usually have this kind of striping. You can see this vertical striping in the data. And we're actually applying two ways of filtering the cube. We're using a Gaussian filter in one dimension, and we are also using a Fourier filter in the Fourier dimension of the image. So here you can see, maybe, I don't know if it is clear enough, but you can see how the stripe in the cube is kind of disappearing, or at least is getting less visible in the image. So this is kind of a nice improvement to the original data. In this way, we can really see better what is happening with the surface. So this is a first step of the tool. Well, we have some comparisons between the profiles of the data. We can also see that we are not losing any information, actual information about the surface using the filters. And eventually, once we have this filtered cube, we need to do the continuum removal. So the continuum removal is an important step in order to analyze hyperspectral data. And the usual technique that has been applied for the NCube and the Moon is the use of linear fits in the absorption of 1000 and 2000. This is because the minerals that are common in the lunar surface, so pyroxene, olivine, well, the two types of pyroxenes can be usually identified in these locations. So the convex hull is an interesting method because it allows the automatic interpretation of the position of the bands. So usually when one does a linear fit continuum removal, you will select the windows where you do the removal, but in this case, the convex hull can do this step automatically. So it will select the position of the band dip, and then it will subtract the continuum. This is interesting because once we have this continuum removed, we can generate different set of indexes. So I will not enter in detail, but for example, we can have the band center. Oh, sorry, this is the olivine index. So we can see locations where olivine is present. We can also have different RGB composites. So for example, this is one that highlights the composition, the presence of spinel and orthocete and pyroxene. We have the band minimum around 2000, 1000, the band dip. So basically, the idea is to replicate all the indexes that we can find in the literature, and that can give us information about the composition of the surface. So here you have some examples of the indexes that we have in QGIS. I will not enter in detail, but as Giacomo was saying, the idea is that eventually this will be all available in the Explore tool. This notebook that is using the Jupyter Hub is also in development, but eventually it will also be available for the public. And yeah, so basically the idea is to have this tool. It will be open source, so everyone can access, and you can work with any NCube data that you want and have all these indexes. So yeah, that is basically it. Thank you for your time. And if you have questions, or eventually if you want to communicate with us, yeah, you can just contact me with this email, or Giacomo, or any of the team. So thank you.
Thank you, Javier. This is a nice unexpected addition. Any questions? Okay, so thanks again for joining, and remotely or in presence. And I think it's time for lunch before restarting our brains for the afternoon. Thank you, everyone, and see you in the next sessions at, I don't know, at 2. I think so. Thank you.